Okay, now I've unmuted on Zoom. I don't think it's amplifying me very much in here, but I think hopefully the people on Zoom can hear me now. Can I get maybe a thumbs up from some of our Zoom friends? Okay, thank you. Excellent. So if folks in the room are able to hear me, I think this will work. And our speakers will also use an appropriate volume of projection for the room, but then the microphone is necessary for our Zoom colleagues to hear. Excellent. We are all very good at IT today. So I'm Meredith Rawls. I am a research scientist at the University of Washington. I work for the Rubin Project, and I also co-chair a portion of the IAU Center for the Protection of the Dark and Quiet Sky. And it is with both of those hats on that I've convened this session on satellite streaks and glints and how they're going to affect Rubin. During the session today, the approximate plan is we'll have some talks, and then we'll have all the speakers come and sit up front, or one of them is online, and we will have some Q&A. So if you have burning questions for the speakers, you are allowed to ask them. But we'll keep that short so that we have like a full half hour at the end for a more interactive Q&A. I also want to thank Peter's hiding in the back over here, but benevolent online mediator. I don't know what the right set of words is, but he will be taking a look at the designated Slack channel for this session so that if y'all want to have asynchronous conversations, the Zoom chat is not the place for that because it may not even exist and the people in the room are not on the Zoom. So if you would like to ask a question, answer a question, start a thread, have a debate, have an emoji contest, whatever, that Slack channel on the Slack workspace for this conference is the place to do so, and Peter will help you be kind to each other and also help let us know if you want to participate in the Q&A. Awesome. All right. Let us continue. So, standard reminder slide. There is a code of conduct, and if you see issues, those are the people to reach out to. If you are feeling sick, please act accordingly. There's a lost and found situation. And sometimes people get a little worn out, so let's be kind and respectful about that as well. Use the microphone. We already covered this. If you're on Zoom, stay muted unless you're talking, and there's a Slack space, and you should use it. Wonderful. I also already said a lot of this. This is the welcome part. This is where I'm talking at you. I'm also one of the speakers. Spoiler. We're going to have talks. We're going to all keep it to 10 minutes, right, friends? And then we'll have plenty of time for more discussion at the end. Excellent. All right, so I want to welcome you to our crowded low Earth orbit environment. It's been a very interesting several years watching Rubin ramp up to become real. Super cool. We're like a real survey when there's not a storm. And also the satellite population increasing rapidly. You'll see several people have a plot showing line go up, so I didn't put my own because you'll get to see there soon. And even just this month, interesting things have happened, which we'll hear more about a bit from Tony and others. But there's this new reflect orbital satellite was just approved to launch as an experiment, a single one. What could possibly go wrong? Just on Friday, Amazon decided, hey, how about 5,000 more satellites? So they just applied for that. Because they recently merged with Globalstar, which has like a dozen satellites. And they're like, well, since we're you now, how about 5,000? Because everyone loves that. So it's interesting times. So we're coming to you with kind of lots of things are changing and Rubin is happening. And we're trying to kind of build the road as we drive on it, if you will. But I want to give you a little orientation to like what kinds of things actually show up in Rubin data, because I know that DP2, like the coads just dropped, very exciting. I will not judge you if you are like scrolling that while we're talking today. But you get everything from like more of a typical streak like you're seeing here. This is what I think most people think of when they think of a satellite streak, the not overwhelmingly bright one, if you can't see where I'm pointing on the Zoom. But then you also get these really bright saturating ones like the one above this one, which I don't know what the heck it was doing, but it was not helping our science. But then you also get these really wide out of focus ones that are not the same thing to detect as the skinny ones. You get some that are so faint, you also don't immediately detect them. And then you also don't get consistent brightness, right? Sometimes they're glinting, sometimes they're tumbling, sometimes they're fading in or out. So any assumption that you may make about, oh, a streak looks like this is probably wrong, which makes this problem extra fun and challenging. So I wanted to give you that as an orientation. Oh, and just as a fun fact, this is an example full frame Rubin TV image from earlier this year. And we did, in fact, check against the public satellite catalog. And there are, in fact, 2 satellites that correspond pretty obviously, in my humble opinion, to those streaks that we saw in the image. Now, why one of them was overwhelmingly bright, I do not know. But we have the capability to check the public satellite catalog and see if a trajectory is consistent with what we're seeing in reality. Sometimes it is, sometimes it isn't. We'll hear more about that later. All right, and I have to advertise, if this is something that you care about, if you find yourself a little depressed after this session, please join us at the IAU CPS. We're working on quantifying and mitigating the problem as much as we can, and we are largely volunteer driven, and we need your help. So you can go to our website, there's a little form you can fill out, you can say, I want to join SatHub, and then a small group of folks, including myself, will say, that's a real person, welcome, and you can help us tackle this. This is one of the cool tools that we're building that you'll hear a bit more about later. It's called Sat Checker, and it's what lets you query the public satellite catalog and say, hey, what is in my field of view? This is showing some actual, the blue ones are ones that are actually in the catalog, and then the red ones are things that we detected in a Rubin visit from DP2. And then this is showing satellite brightnesses over time that we have effectively crowdsourced from a bunch of observers, some with professional telescopes, some with just very experienced eyeballs, all uploaded to a public data repository of how bright this stuff looks over time. Unfortunately, in the last year, that line go up too. So things are not getting fainter or less numerous. So this is the stage that we find ourselves in. And to properly kick things off, I'd like to invite Tony Tyson up to give his talk. And you'll need to stand probably on the, and if you want to be fancy, you can use the clicker. I didn't use the clicker, but you can.
Yeah. Well, in view of world events, my job today is to depress you even more. But I'm actually very excited about Rubin Observatory and the possibilities for science. Given that I have 10 minutes, I'm going to focus purely on what I think is likely the biggest threat to our science in the next few years. No. This is very sensitive. So this is a plot. It's a bit out of date of the number of satellites launched into orbit as a function of time. And you can see that it's going exponential. This is not a linear phenomenon. And Jason, in a meeting that they had a few years ago, said that if you get above about 40,000 on this plot, which we are, by the way, already, as of a few weeks ago, the satellites will start colliding with one another, and they worry about the so-called Kessler syndrome. And this is an announcement that came out just last week from Scripps News about space as a growing concern and plans to address it, creating an interesting turf war between the Federal Communications Commission and our Commerce Department that would like to. Commerce Department claims that it's their turf. That is to say, near Earth orbit is their turf. And I think that's an interesting point of view because they're interested in bringing back NEPA, That is to say, the idea that the near Earth orbit is part of our environment. So I'm looking forward to watching this play out. Nevertheless, the FCC has given SpaceX authority to launch up to 1 million satellites. Many of us thought that this was just individual Starlink satellites. And I'm sure people in the company also thought that. But in reality, it has turned out that it's going to be primarily these orbiting AI farms, most of them. There'll be a small number of them that'll be new, larger, brighter Starlink satellites. So here's the summary. Within 2 to 3 years from now, and I'm pretty confident, unfortunately, this is going to happen, we're going to have 1 million AI satellites launched into orbit by several companies, but mostly SpaceX. 10 to the 6 tons, 1 million tons in orbit by that point. That's a fairly bright night sky, as I will try to point out. And here's something that was released recently by SpaceX. And I would like to draw your attention to these words: with launches every hour carrying 200 tons per flight. Every hour, they're going to be launching one of these large starships carrying 200 tons. That's the build out. They are building this equipment right now. It's not some kind of science fiction. It's going to happen, and I'll explain why. So this is also from SpaceX. It's a sort of a summary of their launch vehicles that they're going to be using for all of this. The V2s were short-lived. It was an interesting test. The V3s, which you've probably heard about, are currently under test. There was an interesting launch, which I'll show you pictures of, which will get them into two kinds of orbits. They plan some orbits that are at a 30-degree inclination, and then some orbits that are in a 90-degree inclination, sort of a north-south solar synchronous, so-called SSO, solar synchronous orbit. And to build out fully, they need the V4s, which are being built, but you haven't seen any of them being tested yet. But just you can look at those numbers in the table. It's a lot of hardware, very fast. So orbit raising is an issue. So something happens when all of these companies raise their satellites. They pause at a certain point in order to test them. They're not going to be raising their satellites up to full operational orbit, because some of them, actually, many of them don't actually work, and they have to deorbit them. So they raise them to this initial testing orbit, which is around 250 kilometers or so, where there's enough drag that if something really goes wrong, it'll just deorbit on its own within days. And they have to do this with every one of their satellites. So imagine if they're launching 1 million satellites, there's going to be a huge pileup, a traffic jam at this place. And it creates a bright lane in the sky, which is a permanent feature which we can't avoid. It's sort of like having many, many moons right there and scattering and making the sky bright. And it'll saturate many of the CCDs in our camera. So this is a drawing by Hugh Lewis based on some SpaceX data. They have to dissipate a lot of power on these AI satellites. So the issue is, let's see if I can use my, no, I can't. The issue is that there's a giant radiator, which is shown in the middle of the upper part of this plot, that has to radiate all of the power that's dissipated on board, and it has to do it very efficiently. And it's white, and it's Lambertian profile, and it reflects a whole lot of sunlight. And I'll get to that in a minute. That's the largest component. And then there are these huge solar panels, and they also have light, also light reflected from the back of the panel and reflected from the front, and then a light that is coming through the panel in the spaces between all of their little silicon solar cells. Those three are important, but it's not the major component to the brightness. And so on the bottom, you can see the size of the V3s, which they've been testing. So here's a picture of the, this is from SpaceX, a picture of their LEOSat solar synchronous orbit satellite. And they have been really trying hard to mitigate the effects of impact on our observatory and other ground-based observatories. And so you see that right in the middle, sort of pointed towards down and towards you and down, that giant 120 square meter white, bright dissipation radiator. And they've been really clever. The idea is that they'll orient this so that it's sort of knife edge onto our observatory. So you can't really, you just see the edge of it, which is negligible, right? It's a great idea. They're trying really hard. The problem is that all satellites that we know about have panels that are constantly twisting and moving because of solar effects, varying degrees of illumination. And there's a mechanical natural resonances of these panels that cause anything that it's carrying to wobble. And as far as we can understand, this is going to be at least plus or minus 5 degrees for these satellites. And so we did a calculation, and others have done the calculation, which I'll show you just in a second, of how big that effect is, and it's the majority of the effect in terms of our apparent brightness that we see. So this is another calculation by the same thing by Ollie Heinout, where what he calculates is the effect on Rubin Observatory neglecting this effect. So this neglects the effect. This is just the solar panels alone and the rest of the satellite. And you'll notice that what he, down in the lower right, what he's assuming is that at 550 kilometers orbit height, the end result is a 6th magnitude satellite. Bear in mind, there are going to be a million of these, but each one is 6th magnitude. In fact, it's minus 1.4 magnitudes because of this other effect. So it's really, each satellite is really bright. That's one issue. The direction to the sun, by the way, if you're curious, is right down here where this little solar sun marker. And all these sort of half circle red things are parts of the calculation that he did where he was saturating the pixels, just the parts that were saturating individual pixels in the camera. So basically, much of the focal plane is lost for anything that's in here, with the assumption, incorrect assumption, that it's 6th magnitude. Imagine this is going to fill in basically if it's minus 1.4 magnitude. So pretty much everything in the sky, except for the part in the upper left, which is shielded by the Earth. So a single LEO V4 SSO satellite at 700 kilometers in our calculation. Starship V3, when they start in another year or two, will launch 15 of these AI satellites per hour. That's 130,000 per year. Each individual exposure would have about 300 streaks in it, some saturating the entire CCD. This is incompatible with LSST survey, needless to say. And in addition to all of that, they will pile up at this low altitude testing pause where they deploy everything, just test everything. And there are going to be 2,500 of these per week combined to create an ultra bright lane in the sky. When they eventually get to station, the ones that are working, each of these 1 to 2 ton satellites can produce very bright glints, as bright as Venus, because there's certain angles where it reflects off different components. And then ultimately, there will be many such orbiting AI data centers, as you heard from Meredith. There are additional impacts of future AI satellites in LEO. The bright lanes in the sky due to pileup of satellites prior to orbit raise. The light from these lanes can saturate CCD arrays. They're going to be a full distribution, a spectrum, if you wish, of glints from thousands of satellites distributed over the sky at all times. And finally, of course, satellites must be deorbited when their AI hardware becomes obsolete, which is every few years anyway. So you all saw this maybe last week, Starship B3 test launch. That's on launch. This is on splashdown in the middle of the Indian Ocean. It went perfectly for them, and they are now planning another one, and then more following that on a fairly rapid schedule using bases in Florida as well. So they're in a full development program on this. So my immediate summary of this is that these AI constellations will actually happen, and they're going to happen in 2 separate phases, one with V3 and one with V4, which is the build out. V4 is the 200 tons per hour launch every hour. And it's not a question of business model. All of us thought, oh, well, this is a Ponzi scheme, right? This is going to fail because this is an obvious business model failure. That's a moot question because it's a lousy business model, and Elon admits this. That's not the point. The point is that the company has the money to do this, and they're just going to do it. They have plenty of funding to do this, so it's not a business model question. They have funding to proceed, and they're going to proceed. So having depressed you about that, let me try and, I can't talk about all the bright satellites, but let me try about, thank you, Reflect Orbital. Thank you, Meredith. This is a picture of the Reflect Orbital group with one of their first satellites. It's sort of smaller than the ones they're going to be launching, but you can see how crinkly the reflecting sheet is, and that's going to scatter light over a fairly wide range of angles as it reflects light down onto the Earth for various purposes. And here's what they claim it's going to be looking like. So you're going to have basically many moons in the sky continuously. So LSST will see many moons on the sky. And this is what Oliver Heinout thinks it's going to look like from his perspective, and he agrees with us. It's hopeless. So FCC has rules for going into orbit, and here are the rules. I won't read every word to you, but basically they're primarily interested in creating a business model for space for everybody. Space is business, and that's what they're trying to promote. And so all operators have to get on board. Basically, the idea is that if you want to operate a satellite or a constellation, you better be in the room, because if you're not in the room, your investors are going to scatter, and your company will fail. And so this is a way of locking in that process. So here's my summary. major impact on optical astronomy, and just a couple of years on from now, the Kessler syndrome is much more likely. Orbiting data centers are not compatible with legacy survey of space and time. And we all truly feel that reflect orbital is a failed business model and probably will fail. But FCC actually will require launches of all these initial phases for all of these proposals. What happens after that will depend on the FCC in the future and the Commerce Department. And with that, I think this is my, last slide. Thank you. This is much more reliable. Use that. Use the button. Right.
Oh, well, thank you, Tony, more or less. I think for the sake of time, we're going to move along and save questions for asking all of us at the end, because I'd like to invite Nayan Jangid to come up next. Nayan is a graduate student in the University of Illinois, and he is going to be telling you a little bit more about some work we've been doing to get a better handle on the I could find the right, there it is, right screen, about better handle on what the impact of these orbital AI data centers, a hypothetical 1 million of them, that could never happen, what that might look like to Ruben in a little more detail. So.
Good afternoon, everyone. First, it's my pleasure to present my work at RCW. Today, I'll be talking about impact of orbital data centers on Ruben. So first, like many operators have either signaled or filed for a orbital data center reaching over 1 million. And if all of these data centers are deployed, they will contaminate Ruben data at a scale that we have never seen before. So our main goal of this study was to understand how the impact of this data center will look like in real life. So before going into the results, I will first briefly walk you through with the method and the brightness model that we implemented. So first we grouped 1 million data centers into 94 different shells according to the table below. And we use Ruben opsim pointings from version 5.3 and propagating all 1 million data centers for over a whole year, it's a bit inefficient. So that's why we did a first pre-filter where we just propagated one representative satellite from each plane and then checked if that satellite is within 5 degrees of the pointing. And then we flagged that shell for that pointing, so that in the next step, we just have to propagate those shells for that pointing, not the whole constellation. So after doing that, we convert the positions of these satellites to local frame, that is azimuth and elevation, and then using our brightness model, we calculate the brightness. And then we also calculate surface brightness and the estimated pixel loss. So first, the brightness model. For brightness model, we use BRDFs, and we use BRDFs from Starlink satellites. For bus, we use Starlink V2 Mini BRDF. For solar array, we use Starlink V1.5 BRDF, and for radiator, we consider as a Lambertian's surface of albedo 0.9. The figure on the right is one of the generated image of AI data center, how it might look like. As for the orientation, the chassis always looking towards Earth. A solar panel is offset by 20 degrees from the direction of sun. And for radiators, it's perpendicular to both the direction of Earth and direction of sun with 5 degrees of offset from the direction of sun to consider the wobble effect. Now the results. Okay, so the first question is how often a pointing will see a sunlit satellite. So the plot on the left shows the number of pointing per day over the whole years, and in that the blue bar shows the total number of pointing per day. and the light red bar shows the number of pointing having at least one streak. It might be illuminated or not, but the dark red one shows the number of pointing which has a sunlit satellite. The bottom plot is just a percentage of pointings. It's the same thing. So during the whole year simulation, what we encountered was around 20% of pointing per night had at least one sunlit streak. And over the whole year, on an average, nightly there were around 60,000 illuminated streaks per night. And on the plot on the left, on the right shows how the night sky might look like from Rubin Observatory. So the outer circle is the horizon. The center of the circle is the sky strip overhead.
I'm confused. Those two numbers don't seem consistent. We have, say, 1,000 pointings per night, and 20% of them have a visible streak. Then where are the 60,000 streaks?
So this is just an average, like over the whole year. Over the whole year, we encounter like 9 million streaks, and I just divided it for a number of days. It's just an average.
Okay, you would think with that, if you have 60,000 streaks per night and 1,000 images, how can only 20% of them streak?
So during the deep into the night, like most of the satellites are in our shadow. So there are like bunch of streaks during the twilight, and like almost like if you consider like there are 60,000 streaks per night, so most like 90% of those streaks will be during the twilight period.
Those images during twilight have many thousands.
Yes. So the plot on the left, basically in this plot, all the colored satellites are the sunlit satellites, and the gray ones are in shadow. So this is basically how the night sky will look like. So next up is the simulation of like how the night sky might look like from Rubin Observatory. So as you can see, like these two bands, which are like green and blue, those are sun synchronous satellites. So those satellites stay sunlit even in the deep into the night. So those satellites are like they disproportionately contributes to pixel loss and the sun streaks, satellite streaks. Okay. Now the next question is how bright these satellites might be. So the plot on the left shows like on the y-axis is the time of the day, and y-axis is the time of the day, and x-axis is the date, and the color shows how bright the satellite will be. So as we all expect, like all the bright satellites will be during the twilight period, which we can clearly see in that plot. During the twilight period, like the brightness is way higher than during the middle of the night. And there is one more interesting feature in one more interesting thing about that plot is like during the southern summer, on an average satellites are way brighter than during the winter period. And the brightest streak that we encountered during our simulation was around 1.3 AB mag. Just to note, this is not the brightest satellite can get. It's just according to like our orientation that we assume for the satellite and the pointings that we have. This is the brightest that we got. The brightest satellite that according to our model that it can get is around magnitude 0. The plot on the on the right shows the histogram of the streaks, histogram of the brightness of the streaks. In that, like all the like lower magnitude streaks are mainly due to the large solar panels. And there is one peak around magnitude 6, which is mainly due to around like the chassis. The brightest the chassis can get is around magnitude 6, the chassis itself. So around magnitude 6, that effect starts to come into picture. That's why we can see the peak around magnitude 6. And as I said earlier, we encountered around like 9 million streaks in total over the whole year of simulation. And out of those, 83% of those streaks were above recommended limit of magnitude 7. And in that, around 230,000 streaks were ultra bright streaks, which are above magnitude 2, which can kill the whole CCD. Okay, so the plot on the top left shows the mean surface brightness of the streaks, and it has the same features as that of AB magnitude plot. Like the streaks are bright, streaks are only visible during the twilight period, and the brighter streaks are during the summertime than in winter. But if you see, there are like, due to the sun synchronous, there are some pointings during the middle of night which also had some visible streaks. That is mainly due to sun synchronous satellites. The plot on the top right shows the number of streaks per night versus day. So in that plot, the green bar shows basically those are the faint streaks. Those streaks are too faint to seen by Rubin Observatory. And the blue one are the streaks which are unsaturated streaks. For those streaks, we are masking only 10 pixel masking width of only 10 pixels. For orange ones are basically the streaks which will saturate the pixels. For that, we are masking 500 width of pixels. And the red one are the ultra bright streaks, for which we are just masking the entire CCD. And the plot on the left bottom shows the pixel loss, and it's in the percentage. So on an average, like again, the same trend, like the pixel loss are only during the twilight period, but on an average, the pixel loss are somewhere from 5% to 10%. But there are some pointings where the pixel loss is about 90%. The maximum pixel loss for a pointing that we got is around 97%. So, and like the higher pixel loss pointings are mainly due to the pointing itself. The observatory is looking in the direction where a bunch of satellites are widely spread out over the whole field of view. So we also did the whole simulation for OPSIM version 5, just to compare like different pointing schemes, like how the results differs. And we also did it for 10% of deployment scale. That is for only 100,000 satellites. So some of the interesting data is for mean illuminated streaks for OPSIM version 5, which was around 88,000, which went down to 60,000 for version 5.3. That is mainly due to because version 5.3 has 10% less pointing itself. So there are less pointing, that's why the number of illuminated streaks also went down. But the interesting part is, even if the number of streaks went down, the percentage of the satellites which are brighter than magnitude 7 remained almost the same, which is for version 5, it was 86.8, and for version 5.3, it is around 84% of the streaks. And all the numbers for 10% scale is the 10% of the numbers. Like number of illuminated streaks are just 10% of whatever it was for 100%. But the most important and the interesting numbers are the bottom one, which are mean twilight pixel loss. So for version 5 at 100% deployment, it was 7.6% on an average. For 5.3, it is around 7%. But even at the 10% deployment, that doesn't go down by 10 times. It only go down by 3 times. So for 10% deployment for version 5, it was 2.5, and version 5.3, it was 2.25. So it just scaled down by 1/3 at the 10% deployment. And that is mainly due to the sheer size and the brightness of the satellite itself. So the bottom line is like 20% of the pointings per night will have at least one visible streak. On an average, 5 to 10% of the pixel will be lost during the twilight period, and the brighter parts are the brightest streaks are mainly due to the solar panels. And even at the 10% deployment, the pixel loss is still very high. So this basically shows, even if there are less orbital data centers, they lower the orbit, and with the different scheduling schemes, there is still a problems that we can't solve. Thank you.
Oh, thank you, Nayan. mostly. No, wonderful talk. And I imagine many of you have questions for him. Gonna also defer to the discussion at the end unless there's anything super urgent. Okay, we'll forge ahead. All right, up next is me again. I already introduced myself, so I will spare you hearing that part again. But I am actually going to be telling you a little bit about a project we've heard now about kind of future speculative, likely, unfortunately, future things that are coming our way. And I'm going to switch a little bit and talk about what we've seen in the not too distant past, like in actual data. And because Rubin is brand new, we use some DCAM data. So this is a student-led project that an undergraduate exchange student who from Japan who came to visit the University of Washington for the last academic year, Kiyo Okudaira, he cold emailed me and was like, "Hey, I like to track little bits of debris. Do you have anything cool I could do with satellites?" And I was like, "Yeah, you seem to know what you're talking about. Let's see what we can put together." And so this is what we put together. We also worked with Dino Bektezovic, who's a postdoc at the University of Washington. So he presented a poster. There's 3 of us in one place, miraculously, presenting his poster at the UW Undergraduate Research Symposium. And what we did is we took a look at 4.5 years of DCAM images from the Blanco 4-meter telescope in Chile, and took a look at what kind of satellite streaks did it see, because it's kind of a mini Rubin, and we already used it for a bunch of other like Rubin precursor work. So what does that look like, and how can we use that to inform our life choices for Rubin? We have Alex Strelica Wagner to thank for doing some initial linear feature detection on the whole DCAM data set that we used, kind of as an initial like starting place, because we didn't want to try to process every single DCAM image from start, because again, this was supposed to be an undergrad project that was like doable in a finite period of time. But the goal was to come up with a way to reliably detect and compute properties of the streaks that we found, to measure population statistics and to build a catalog so that if people want to go back and look more deeply at any individual subset of the population, they can do so, and then to improve the technique so that we can do this better for future data sets, because obviously, as you've seen, the problem is not going away. So this also built on a couple other past projects that were on that previous slide. So we made a little pipeline. Most of the work was done in notebooks, and we're working on writing this up. It's not out yet. But we first we did some kind of reality checks. We cleaned the catalog to find, the things that where the telescope moved and everything's a streak. Okay, well that's not what we're looking for. Or there was a strange, saturated column, and okay, well that's not a streak that of a flavor that I want, right? So if they were like unphysically wide or unphysically long or like had unrealistic signal to noise ratios, we made some realistic cuts. And then we fit a Gaussian on the streak profiles in little 50 pixel segments. That's what you're seeing here. So along the length of like a full streak, we chunked it up into little bits and fit Gaussian profiles, which is not exactly the shape that they are, but it was a thing to estimate the width. It's not supposed to be a perfect fit. And that lets us come up with a way to say, hey, there's definitely a streak here. This is about how wide it is and how many pixels we'd have to like ignore, throw out. And we can then try to measure brightness within that rectangular aperture. In this particular example, the outliers are because there's a streak in my streak. So welcome to my life. Another interesting situation that we found was here is a little chunk of a DCAM detector that we found. And it was like, okay, well, there's like a bright blob in the middle. Was it flaring? Because this can happen, right? It can rotate, or something weird can happen with a glint, and it can like get bright for a second. And so that also was an outlier in our fitting process. And it was like, well, wait, can we see, was any other image taken of that same period of sky or same chunk of sky like any other time? Yes, there was, with a different streak, and that was actual astrophysics that was blocked. So I'll go back. So that's actually a little galaxy friend that you can no longer science. And we demonstrated that here with a different streak instead. So that was the kind of thing that we had fun doing. The final steps of our pipeline were we did I'm going to say just real simple rectangular aperture photometry. We drew like a box for background above and below the streak, and then we drew a box on the streak. And then we used the provided photometric 0 points that are not perfect, but they were something. And then we also identified the streaks that we could using the sat checker tool. And here's an example. There's a little tiny little black streak right here, which is hilariously not exactly in the detector box because the WCS is approximated linearly wrongly, but you can pretend that that little stripe is actually exactly on the tiny box. And then if you had to guess which of these catalog streaks corresponds to that little black line, you'd probably say the red one, and I would too. So we wrote an actual like fitting code that looked for offsets in angle and offsets in translational position. And we did not do offsets in time, but we probably maybe should in the future to match the detected streaks with actual objects. Not all of them had a match, spoiler, but a lot of them did, and that can help us understand like what's causing the streaks that we're seeing in the image. So we have a final catalog that again is not published yet, but it has like the basic parameters that you would expect it to have. So the streak ID, the matched object name if it exists, what exposure and CCD it was detected in, how bright we measured it, if there's any quality flags or issues, etc. All right, so here is one of our results, the streak brightness distribution here. I asked, we need to break it down by band because sorry, DCAM has multiple filters and this is all lumped together. But not actually overwhelmingly bright, interestingly enough. But again, this is 2019 to 2023. This is like a different era than we're in now. So a lot of stuff was fainter. And Ruben also is going to see a lot of faint stuff, which is a whole other separate problem that we don't even have to talk about in this session, but that I'd love to chat with you about later. I drew an arbitrary line at the exact, not exactly, I did this in Keynote. I drew a line at around 7th magnitude, which is the brightness recommendation threshold for how bright satellites should be allowed to be in some perfect version of reality that's actually not perfect, to show you that relatively few of them in this data set are actually what I will call too bright. For what it's worth. All right, another result we saw is not surprising, but it shows you that you get the most streaks in twilight, right? Just what Diane was saying is that, if you're going to be trying to avoid getting a bunch of satellites in your image, you're probably not going to want to take your data really close to sunset or sunrise. Sucks if you're trying to do solar system science. But this is color coded by the orbit the satellite is in. So we matched them using the sat checker tool I mentioned. The blue is low Earth orbit. The orange is medium Earth orbit. The green is geosynchronous orbit. The red is helio. So I don't even know what HEO is right now. Something else. And then the purple is, the gray is something that we actually couldn't match. So we couldn't find a catalog counterpart to that object. There's several reasons that can happen. And there's a bunch of them, obviously, that didn't match. It could be a small piece of debris that's not in the catalog. It could be not in the position it's supposed to be. That happens a lot. Things like that. All right, and then here's another result. This is the sky distribution of all of the objects that we found in this data set. And so I'm not entirely sure why they're mostly in half of the sky. I haven't thought about the geometry very deeply recently, but we broke it out by category. So everything is in the upper left, but then we've broken it down by like active payload satellites in the top middle, and then debris in the upper right. There's some rocket bodies, which honestly are the same as debris in my mind, but fine, you can break that out separately, lower left. And there's a couple things that were actually labeled as unknown, which is very confusing because then we have the like wasn't able to match version of unknown in the lower right here. So you can we found, but a lot of these are actually the same physical object, right? Because a streak goes across the focal plane usually, and there's like multiple detectors that it hits in a similar way for Ruben. And so like the number of unique objects detected is something that we also took a look at. So like 590 some odd in 2019. Surprisingly, there wasn't as much data in 2020 and 2021. I wonder what happened then. And then back in 2022, we had 351 unique objects and then only 87 in 2023 because it didn't go for the whole year. The data set didn't. So this is not this is not answering all of the questions, but I think it's interesting and I think it's relevant for Rubin. We found a total of 9,700 streaks, and we were able to measure brightness for 6,100 of them. Very few were too bright. That's not going to stay the case. And about 40% of them don't have a match in the public catalog. But like I said before, the satellite population has changed really a lot, even just the last 3 years. It's obviously going to be changing more, as we've just heard. And also, Rubin it uses a telescope with a larger mirror, and also there's a wider field of view, and that is also going to change the morphology of the streaks that we see. We need to be able to link the streaks together, right? Because right now this is like 1, 2, 3, 4, 5, 6, 7. This is like 8 separate detections for one of these. This is actually parallel Starlinks, turns out, relatively soon after launch. And obviously this is the same astrophysical object, but Rubin has a similar issue in that we process things one detector at a time, in particular in the prompt processing world. So knowing about like one object that goes all the way across is a little bit non-trivial. And of course they're getting bigger and brighter more numbers all the time. So that's going to be great. All right, I will end there. Thank you. All right, and next up, I would like to invite, I realized I didn't put Adam Snyder's next. Please come on up. I didn't stick your name in here for some reason, but I have your slides. They're just in a different window. Hang on a moment. I wanted to let you use your Google slide deck just in case there's anything new or fun. There we go. Oh, well, sorry. Well, anyway. So Adam Snyder is a postdoc at NORLab and is working with me on trying to figure out what the heck is going on in streaks that we have seen in DP2. And he has an initial report to share. So take it away.
All right. I guess this is the benefit of the Zoom speakers, but I have to remember to pull this up. Yeah, so I'm Adam Snyder. I work at NOIR Labs. I've worked with Rubin for a while. And, we've just looked at some representative results from DECAM, and with the upcoming sort of data preview 2 release, I'm sure a lot of people are interested in how the streaks are affecting or could potentially affect some of the science that you would like to do with that, with those results that are being that are coming out. Let's see. It was a all right, so just sort of like a quick overview here. I will start by saying that we do perform streak detection and glint detection in some capacity within DB2. However, I will say that the artifacts of these algorithms are sort of minimal as of now. And largely localized as different sorts of flags. So pixel flags, for instance, associated with objects that look like streaks, or even source flags. So flagging sources in their catalogs as potentially being parts of glints or trails and things like that. For those who are not familiar, Data Preview 2 includes science images and some additional images taken between roughly April 2025 and January 2026. If you have some familiarity with the Butler, maybe these would make more sense. The difference images, so these are basically our visit minus some sort of sky template that captures the more static objects that are in that area. I included the Butler dataset name, and then of course the other one is this catalog of DIA sources, so the difference image analysis sources identified within these difference images as a separate data set. All right. I'm not going to go into details on exactly what's being done. I've just highlighted it here. I think the more important thing is the output. So what we get from from the streak detection, I'm sorry, to clarify, this is just for the streaks. I will touch on the glints in a little bit. You get within each detector image, so your visit image associated with that, you get pixel flags that are marked as streak, and they're labeled, and then that is propagated along with other similar pixel flag labels associated with saturation, diffraction spikes, instrumental effects. This is all propagated downstream, and this becomes it becomes a little muddled because, of course, there's this very large pipeline that these things exist in that it does propagate down. But that is essentially, if you want to find the sort of impact, this is where you would look. The second thing is that we do have built-in handling of sort of an output dictionary of what we've identified as being potential streaks. It is not persisted by default. So if you are going to try and dig through DP2 to try and find this, unfortunately, at the time, you will not have access to that additional data. And this is something that will be addressed moving forward. So here's kind of the overview. What did we find? So each detected streak has a line parameterization associated with it, in this case, a Hess normal form. And the Gaussian fit parameters. So again, we're fitting sort of the cross-sectional profile, so cutting straight across the trail of the streak. We're fitting that a Gaussian to this. Again, this is, I pointed in here, we treated more as proxy variables since we're sort of assuming that it's a Gaussian shape when it may not be. But these are sort of our proxies for how bright are they and how wide might these streaks be. So here's a large table showing the streaks that we've identified, so the total number, total per filter band, and then the visits for reference and sort of a rough estimate of how many we expect. And you've probably already noticed that down here in the Z and Y band, there's a huge uptake or an uptick in the streaks per visit, and I will get to that in a second. So here I've broken it down into two histograms. Now, for historic reasons, there are two types of sensors that make up the camera focal plane. So I've divided these out. We know that there are, slight differences between the two. As it impacts streaks, the biggest thing is different instrumental effects and how those might bleed through as false detections. And again, if you remember, that Y band spike is quite obviously isolated within one type of detector, those manufactured by ITL. And you see this giant spike in the Y band. So this is the stacked histograms. And again, I've divided these out by bands. They look fairly similar in their distributions, modulo, maybe some humps here, or smaller spikes within them. But this is probably the largest effect is whatever is happening with these ITL sensors. Yes.
Is that the channel stop fraction that it's accidentally picking up?
So actually, I can't quite tell for certain what it is. I have some ideas, and I believe it may. What I initially thought within the past weekend was that this was associated with a particular ITL defect that I will highlight later. But while searching to try and find a representative, I found a couple other interesting examples that are very different, but they may be related in some manner. So I can't say for certain, and this sort of gets back to we don't have quite enough metadata attached to these streaks to be able to, sift through enough and be like, that's the effect that's causing it, or this is exactly a spike and things like that. Okay, I'm sorry. So this is the distribution of the widths, essentially, the Gaussian sigma in pixels. And then I have replicated this with sort of our proxy for how bright they are. Again, there's this large spike, so it seems to be some sort of distinct population. And again, some differences in here. For instance, the ETV seems to have some population of detections at a specific, between 1 and 10 nanogenskis. I guess that is maybe an instrumental effect, or it may be associated with something else. Okay. So this is sort of our, people like to talk about the pixel impact. How many streaks do we expect to see? How wide will they be? How many pixels may we end up needing to flag at least? So that's what's being represented here. Again, there's a lot of these similar effects within the populations themselves that are driving these numbers. Okay, so now let's get to the examples, because this is probably a more interesting thing. What are these detections? What are we finding? So this was teased a little bit. We do know that there different sensors have different instrumental effects. So one of them is this thing called ITL dips that results after a very bright star is imaged. I won't go into the details about what exactly that is, but it causes a defect that runs along the column. So naturally, running along a column looks like a line. It's going to be detected as a line and will be propagated downwards. So here I've only highlighted sort of the start and the stop extent. Hopefully it shows up well enough. You might need to go to the slides to see the actual the dip itself. So this is a negative dip, but a linear feature that's being detected here, as some sort of thing that we believe is a streak. And this is one example of an instrumental effect that can bleed through. Yes.
So you're doing negative streaks as well as positive streak?
Yes, it does. It's just, so it's looking for linear features. There's no like a signal.
But you're
Really?
looking above the detected pixels, and I guess you're doing detected negative.
So it's detecting the edges
Okay.
of
some
this.
the tips
So
have
yes.
Wash of things.
Yes. So that's actually what it is detecting. So it's not detecting one line per streak. What it is actually finding is two lines on either the boundaries of the streak that associates with a single instance. So in this case, you have two slight jumps, within a dip, and that's two lines, enough to be identified. Here's an actual detection, but this also highlights one of the other shortcomings, unfortunately. So this is a detected streak. You can see at the top, it only spans about 600 pixels into the detector itself. But how streak detection is done is that we're assuming that the streak or the line is spanning the entire detector. So that's why the bottom half of the detected line is way down here, but you can see the streak has cut off at some point. So maybe flagging the entire extent of this line, we're actually counting, more pixels as being removed or being flagged, I guess, than really need to be. And then this is actually what I found this morning, was trying to track down and actually confirm that what I had thought that population was this ITL dip phenomena. But what I actually think is happening is this is unfortunately an image, a pathological image. I believe I think Craig said it related to the tracking.
It was a fault.
Yes.
Stop tracking in the middle of the.
Yes, but as you can see here, there's a lot of things that look like lines. So it spits out a lot of line detections. And this is actually what I believe is causing that huge spike. Now, why it's only in this seemingly in wideband is still a mystery.
If it's one image, like you should have, I don't know what selection you did for the visits that went into this.
This is everything that's in DP2. So if you go.
Yeah,
This made it.
Yes. Well, so, all right, before everyone panics, all right. So like I said, I stopped at the different images within DP2. Now, of course, there's extensive downstream processing that goes into further data products that I, unfortunately, am not familiar enough to say with certainty that this is being removed over the course of that analysis.
Well,
I do not know.
Somewhere, but
one would hope it's being removed.
Was in the.
It made it, yes, it has. I've seen it show up on a few. There's a collection of basically like a table, a CSV table of visits that have been, people have found that have said like, oh, this was a failure in tracking. All I can say for certain is if you go to the butler and say, give me the difference images.
collection, is this on?
DP2 prep, DP2. Yes.
Did it get synced?
I think
Because
so.
we had a lot of.
I know.
We don't want.
This, yes. So this is something that will certainly need to be followed up to make sure that images like this are properly handled. But if they are not, for whatever reason, or you get something like this. And also, this is one detector, so all the detectors are like this. So what I'm thinking is there was probably some nights scheduled for wideband imaging where there was problems with the tracking. So many of these images And that's why there's this huge spike in Y band associated with these.
That one.
It might also just be a few of these too, because this is an enormous amount of streaks with this. So again, this, there's a lot that needs to further go on. But as I said, a lot of the artifacts are only flags. We do not remove these, right? Now, maybe that causes you more worry. Maybe that like we aren't removing the true streaks in some manner, but in cases like this, this is clearly some other failure that's being, muddying the identification of, what are true streaks, what are false detections, what are some other instrumental effects. So I believe, all right, so very briefly, Glints. So similar processing goes with Glints. The biggest thing are that the Glints are being detected essentially as sources that seem to coincide along lines. It does some algorithmic matching, proceeds iteratively through this to try and say, okay, there's such and such number of sources. They all seem to lie along this line. It resembles, some tumbling artifact that's producing, this string of pearls, I guess, is usually how it's described. Again, there's some parameterization, but at the end of the day, what happens is in your catalogs, you get a flag, so a column that says, is this associated potentially with a glint? Yes or no? And that's what's in the database. So just sort of naively looping through all these, I found an order of one of the, or either not 10, whatever, a lot of DIA sources, much less flag sources, says 8.6%. But I will caveat this by saying that within crowded star fields or fields with just a lot of objects in them, you're almost guaranteed to have a few that lie close to a line. And if you're not careful of how you're doing this actual detection, you're going to get pretty much everything in a crowded star field flagged as a glint, because it's almost certainly there's another few that are lying close enough to any sort of line that might pass through that one. So this is just a brief discussion. Again, glints, they're flagged. They're not removed later. These flags may be propagated downstream as well. All right, so I think I'm probably coming up on 10 minutes here. Again, reported impact is minimal. The underlying pixel level effects are not analyzed quite in the detail I personally would like. So things like variability, segmentation, so not necessarily spanning the entire detector. Something may break up, but not break up in such a way as to be a glint. There's sort of like this intermediary where you have sort of like this progression from solid line to dashed line to dotted line to eventually, maybe one or two objects and things like that. And these are difficult things to handle. This classification, true versus false. We do not form, or there's no visit level merging. So these are just streaks per detector. Now, a streak that spans the entire camera field of view will be detected on every detector that it passes through. So this is not necessarily a measurement of unique sort of objects passing through the camera field of view. It's that times however many detectors it passed through and was detected on. So there's a lot of work kind of going on behind the scenes. The biggest thing I think is including additional mask planes. By default, we're missing two that I think are very important. The one is this thing called spikes. So these are artifacts from really large diffraction patterns. Again, things that are pointed look like linear features. They get detected as streaks. Again, the ITL dips, that should remove at least that instrumental effect. I would like to, there's certain improvements to how the streak data set is persisted. As when I first introduced this, it's not. Even if we did persist a dictionary, that's a little bit harder to handle. So I'm sort of exploring routes to expand toward treating streaks more in the same way that we treat sources. So building catalogs with a lot more metadata behind them, things like footprints as well, that allow you to go back to what you believe is a streak, associate it with the actual image pixels, and then perform more complex analysis to allow you to do things like segmentation, classification, merging, stuff like that. And then finally, there's always this search for, can we improve the algorithm? So building off of the current algorithm, which is a Huff-based transform, I've actually tested out a few. I think this is the most promising, is this radon transform-based method. There's a lot of information that this can encode, and it treats, it helps address some of the issues that we're having with things like variability and segmentation. I'm not going to say it's going to provide all the answers, but I think it's worth exploring to help, build out a better ecosystem for how the streaks are being handled within data releases going forward. And I believe that is my last slide. It is. So hopefully I did well on time.
All right. Last but not least in this session, we have a talk from, that's my, you don't need to see that. We have a talk from an online person who I will unshare my screen so that she can share her screen. So the next speaker is Michelle Dadagat, who is a software engineer at NORLab who's been working with the IU-CPS Sat Hub to develop our software tools. She's been really instrumental in building StatChecker and SCORE. And yay, and she is online and she has slides and just even a box on the side for people who are here in the room. And she's going to tell us a little bit about Attitude Checker and StatChecker and how they might be able to help in some situations. Go ahead, Michelle. I will let you know if there's any audio problems on our end.
Okay, well, there's going to be an audio problem if I don't unmute myself, but hopefully you can hear me.
No, you're good.
Okay, cool. So I think that intro pretty much covered it. These are a couple of the projects that we've been working on with like as part of Sat Hub and IU-CPS. One of them has been mentioned already, and that is StatChecker, and that is the API for satellite position prediction. But we're also working on another one, which is a concept called Attitude Checker, which screen over here. I'll explain that one in a minute. So obviously from the deluge of evidence already that you can't avoid all the satellites, but in theory, there are some steps we could take towards mitigation of some of the brighter passes, especially with some of these things like Reflect Orbital or just some of the space mobile ones that are just inherently brighter. And two of the things that can make mitigating a percentage of those passes possible are better precision with position predictions, and also storing upcoming passes or intermediate calculations in order to make this possible, because right now propagating all these objects for every observation over the course of a night isn't really feasible for the scale of scheduling that Ruben has. The other one is making the overall zones in the sky that are part of upcoming observations available to operators if they're able to make attitude adjustments to spacecraft passing over that in order to at least reduce the brightness of certain objects. Let me see. There. So I just realized there. That was odd. The current state of StatChecker, in case wasn't covered by any of the other presentations, is basically just an API to calculate the satellite passes through a field of view from publicly available catalog information from SpaceTrack and CelesteTrack. But right now it propagates everything and it filters by visibility through that field of view. So it's difficult to use for, hundreds of observations per night, because it's only one field of view per API call. And even if that changes in the future, that's still a lot of calculations per field of view. And we recently just added the ability to refine Starlink positions with ephemeris data. It's optional only right now, but it still uses the TLEs as a first pass to see what's in your field of view, and just to make those positions more accurate, because there is a decent difference between TLE positions and ephemeris positions. I think This slide has I think one of the clearest examples, even though I don't remember the scale of this one. But you can see, so like the green triangles and the red circles pretty much line up, and that almost completely in on track and cross track error. And that is the red ones are actual observations of a satellite, and the green ones are the interpolated ephemeris positions from Starlink. The blue squares were I believe this was a Space Track TLE, so it wasn't the supplemental ones available from Celestrak. But some of the things that we're working on to try to improve StatChecker and make it more usable in real time and also more accurate is to make sure that we do use that operator ephemeris data as a first pass of position prediction, but that is only currently Starlink where we can get that directly. We are experimenting with trying to generate TLE data based on that ephemeris data to see if we can get a closer match than Celestrak supplemental TLEs. And the answer is tentatively yes, but the quantification of that is something we're still working on. One of the other things that we can do with StatChecker is we can cache upcoming passes, eliminated passes, intermediate ephemeris calculations, so that when you go to actually to make this, I guess, more feasible to potentially use in a scheduler or something like that, to see if you can actually get more of a real-time answer of, do my next observations actually have satellites in them or not, without having to do propagating for every object, for every field of view. Also, brightness estimations is something that's going to be added, so you can filter by the brighter passes. And I guess this is similar to the other one, but it's not it's not 100% the same. But if we're able to store upcoming passes over Rubin, just the satellite passes for the next night, the next couple nights, then you're just querying that information directly, and that's going to cut out pretty much all of the processing time that we've had to do now, which is the propagation with SGP4. And this is an example of, unfortunately, we do have some of these cached positions right now, but unfortunately we started getting them pretty much right around the same time that Rubin went off sky for the storm. So I haven't been able to double check yet to see how they kind of line up, and just to see with images to compare how accurate this has been. But for a 24-hour period, this is broken down by the object type, the number of objects in that type, and how many pass. And it's not for a night, because this was just for a 24-hour period that I was able to do a quick query for. But if we're able to just compare this list of passes against upcoming observations, or even prior ones, to characterize what was going on, then that'll be a little bit easier. And moving over real quick to something else that we're trying to work on now, which is a concept called attitude checker. And the idea with this is, if there are operators that are willing to adjust the spacecraft attitude to avoid certain zones of the sky to minimize bright passes, this is how it could be done. We generate a HeelPix version of upcoming schedule information with no timestamps, and provide that information to satellite operators. They can query it for what's coming up in the next day. Even though there's no timestamps, it can be cut by 8 hours or 16 hours or whatever it is. But then they can do some part to, I guess, minimize the percentage of observations that are affected. Like, there's no way to eliminate all the streaks, but anything that could be done between these two tools to minimize the percentage of bright passes is something beneficial. And yeah, so the better positions that we have, the more reliable the StatChecker will be as a tool that could be used for upcoming observations, to potentially be used as part of scheduling, because you don't want to make changes to things based on I guess, rough positions. So like the more ephemeris data we have, the more stored positions we have, the more reliable it's going to be. But it's also going to help with like some of the other things that projects that have already been mentioned. We're going back and quantifying what exactly showed up in which image and when. And so the better information we have, the better we can do that as well. And also just sort of open the doors to maybe better, more productive conversations with satellite operators to see if there's something that we can, an agreement we can come to say, hey, if you anything you can do in this one section of the sky, we would greatly appreciate. Here's where it is, here's when it is, and then, you know, just reduce the amount of impacted observations in that way. And I know that was the super, super quick version, but I know that we're short on time, and I think that covers the bulk of the points that I had. So hopefully that wasn't too rapid fire.
No, thank you very much, Michelle. Let's give her a hand. Excellent. I'd like to invite, I know we only have 10 minutes left because I'm too nice. Apparently I didn't kick people out fast enough. But I'd like to invite the speakers here and Michelle to stay with camera on if you're cool with that. We'll come up here, we'll pass the microphone around a little bit, we'll chat. We'll fix all the problems in the remaining 10 minutes of this session. No, we won't. I'm gonna grab my water bottle. And Peter, I invite you if there's things online if you want to. We have a lot of hands in the room too, so this is going to be a fun 10 minutes. Okay, I saw up here first. Yeah, please. And, you know, honestly, we should. I don't know how good the room microphones are, but
Maybe just repeat the question.
Yeah. Okay, I'll repeat the question. Excellent plan.
This one's for Adam. You were talking about algorithms that get rid of what Meredith was calling the typical streaks at the beginning, like sort of the linear, narrower ones. And coming from the perspective of trying to study like individual variable star targets, I'm wondering if there would be a way to tell whether, say, in the case of a more diffuse streak, all the sources in a field might be a little bit brighter. Could there be some, or is there already some sort of flag to be like all like several sources in this field are brighter than their coads, so you should be wary?
Sure. So asking if there's a way to flag like concerning images based on the number of streaks seen in many words.
Number of brighter
or sure, the number of brighter sources seen relative to maybe an expected value.
Diffuse, it might not be a linear streak.
Right. If it's diffuse, it might not be a linear streak.
I will say, right now the things are flagged. I didn't go quite into detail, but basically anything identified as a streak has a flag that's built using sort of the width proxy, so the Gaussian sigma, out to a maximum of 100 pixels. But that is the extent of how they're being flagged right now, and it's also just sort of like a bar. There's no like footprint associated with that. So this is one of the things that I'm working on, is moving towards treating streaks almost the same way as we treat sources. So this sort of diffuse background would essentially boil down to a similar thing occurring if you were just in a large crowded field, right, with multiple sources contributing to the background. What I'd like to see is move towards the same tools on how that is addressed. If we can treat the streaks not just as a linear line, but as a source itself, because it has a shape, it has, you know, variability to it, and sort of flagging not just a bar, but these are the extent of the pixels above even a potentially lower threshold, or allowing for more intricate, detailed measurements based on that, you know, shape measurements, for instance. Things like that. So I think this is something to explore in the future, because as I said, now you only get a flag. You get true or false. Basically, is there a streak in someone in the region? Yes or no? And it seems that we would like to make, you know, improve on that. I think there's a lot of work that could be done there.
Oh, thanks.
If I can elaborate just super briefly, what exists in DP2 exists in DP2, and it is not perfect. It does not include the faint things. It does not, right? It sometimes we are saying, hey, there's a source that isn't a likely glint, but it's actually a crowded field, and like it thinks everything is glints, right? So it's Adam has a lot of really great ideas for how to improve our streak and glint detection that we're going to be working on, that we can hopefully implement in time for like DR1. But there's a lot of work to do still. So yeah.
Thanks.
Yeah.
Yeah. There's something on my mind that I really have to comment on, and that is Michelle said that there's some chance that we could avoid if we knew in advance that there was a really bright satellite coming into our field momentarily, that we could avoid it. And we showed in SATCON 1 ages ago that that's not possible if there are more than a couple of thousand satellites that we have to avoid, because if we're going to wait for 10 or even 20 seconds for it to clear, we would never open the shutter. And now with at the moment, I think that what she said would actually work, because at the moment there are only 16,000, as she said, satellites. So if you cap the number of satellites at 16,000 and keep it there and keep the brightness the same, then it's going to work. But with 1 million first magnitude satellites, we will never actually operate.
Just a quick note. So during my simulations, none of the satellite had none of the satellite had a specular reflection of the solar panel. So even if like we do some mitigation using like offsetting the solar panel and everything, the brightest that I got was for offset of around 20 degrees. So even you offset by like few degrees, the brightness won't decrease that much.
All right, what else we got? Eli back there.
Yeah, so Tony, you showed that map that said, 100% of the sky is 100% saturated or something like that.
Yeah.
Was that all through the night, or is that at twilight? I wasn't clear about that.
The all sky saturated map, is it always or just twilight? That's the question.
No, it's all over. Yeah, it's not just the low elevation, it's the entire sky.
Yeah, but what time of night?
That was an effect that would appear at midnight as well.
Okay.
Because of SSO. It's purely because of SSO. I have to say, SpaceX is trying really hard to mitigate this stuff, but it's hard to do. So what they're planning on doing is populating different shells. In other words, this also helps to avoid the Kessler syndrome. If you just put all your satellites in one shell, good luck. But what they have decided to do is to put them, this is public, put them into shells that are separated by 50 kilometers. Lots of 50-kilometer shells at each group of AI satellites at each orbit altitude. So there are multiple groups at different altitudes, and within each group, they're going to be populated by these shells. And so we can point in between. So that's about 30 degrees. We can point in between them without seeing them directly if we want to. So that's one of the things they're trying to do, but it's pretty hopeless.
Yeah, another question in the back here.
I just had like a sort of question. Like a question was, so is this problem easier to solve if, in some magical world, the dynamic range of the CCDs was much larger, and we don't have issues with saturation, but we just somehow? Yeah, it took a very random question.
In some magical version of reality, could we design a detector or camera in which the problem would not be as bad? Here, Tony.
So in a previous world, when we're talking about faint galaxies that we need to detect at high signal to noise ratio in order to do our science, a typical Starlink satellite in a previous world, V1, was several 100 million times brighter. And I know of no system, mechanical or electrical, that has a dynamic range that is that large.
Can't argue with that. Yeah, Richard, please.
So
Probably, Tony. Can you give us a satellite physics lesson?
How do you have?
Essentially, all the solar radiation that's actually absorbed has to come back out as heat. And so how does that radiator, which only has about 20% of the area of those giant solar panels, actually work?
Richard would like to understand radiators. I would like to let you all know it's 3 o'clock and you are allowed to leave, but I'm going to hand the microphone back to Tony now.
So they have a fluid. It's sort of like your refrigerator in reverse. So they have a fluid that circulates through the AI chips in contact with that aluminum, and it goes into the radiator and transfers all of that heat into the radiator, which is white and radiates very effectively in a Lambertian profile. So that's the way it works. That's the physics of the radiator. And it has to radiate about a factor of 3 more than the AI computation load, simply because AI is not 100% effective. And the radiator itself is about 0.8 effective.
Do you have a guess what their electronics temperature is going to be?
Yes. It's not too bad. It'll work. Yeah.
Yeah, it'll work. Don't worry about it. Okay, on that cheerful note, we are at the end of time. I think all of us are sticking around this week. We'd love to chat with you more. We'd love to have you join the IUCPS Sat Hub and help us solve all of our collective problems. Thank you very much.